This is Unit 6 if you're with Greene County High School Tigers, and if you are...
If you're with the Falcons, we're Unit 7.
Unit 7, so make sure you're writing that down and corresponding your notes. This deals with states of matter, solid, liquid, and gas, and something really cool, which got a bunch of different experiments, thermochemistry. So, let's go ahead and get started. What is kinetic molecular theory? Well, it has to do with kinetic. Ms. Morris, kinetic meaning?
Motion, so things moving around.
Motion. Okay, so the word kinetic, if I'm up here, the word kinetic actually means motion. And you'll learn this next year when you take physics, or if you're an AP student, you probably already covered it. Kinetic energy deals with energy of motion. And so go ahead and make sure you got that in your notes.
So I want to see kinetic energy written on the key idea side, and then on your notes side, energy of motion would be what goes right next to that.
Perfect. First of all the gases, we're going to be talking about gases, then liquids, then solids, but all the gases, we're going to pretend they're just really, really small hard spheres. So for example, this tennis ball, we're going to pretend this is a gas molecule. Now, from your knowledge of chemistry already, you know certain gases, like H2O, aren't perfectly round. In fact, they're kind of oblong looking, right? So if I drew an H2O molecule, I'd have O in the middle, and this is your Lewis dot diagram, right? H is coming off. This is not round, but we're going to pretend, assume, if you will, everything is a perfectly round, small hard sphere. Okay? Also, these gases are constantly moving. You're going to learn that gases constantly bouncing off one another. Okay? They're just crazy. They're super hyper in comparison to the liquid or in comparison to the solid. And lastly, these gas molecules, these balls, they collide. And when they collide, they're called elastic. Now, this is not the elastic like
rubber band.
Yeah, a rubber band, or in Miss Morris's hair tie, whatever. It's slightly different. So scientists actually have a specific, when gas molecules collide, that no energy is lost. So it's perfect collision. And that's what an elastic collision means. So if we look at this, take a balloon, each little ball in here represents a gas molecule, and they are moving. These are the different motions of the gas molecules. And the fact that the balloon is able to be blown up causes it to, it's due to the impact, if you will, of the gas molecules hitting the walls of the balloon, and that's what keeps it blown up. Okay, so some of the molecules moving kind of fast. Remember, this is kinetic energy motion. Some of them are moving extremely fast, and then some are kind of moving a little bit slower. But overall, there is an average kinetic energy. And you can see here, these are little gas molecules, constant motion. So they're never stop moving. You can see they're going to collide and they just bounce right off each other. This is what's happening right here in this room, all around us, millions, moles, if you will, of gas molecules moving around.
But also notice that you still have different speeds. You've got your slow ones, you've got your faster ones.
Absolutely. Okay, so this is kind of obvious. Let's say we were in this room, and right now it's actually kind of chilly, right? You had to go get your sweatshirt a little earlier. But if we were to increase the temperature in here, all the gas molecules, they would start moving faster. And so if they're moving faster, remember kinetic energy means what, Ms. Morris?
Kinetic energy is the energy of motion.
Energy of motion, so if you increase the temperature, kinetic energy is going to go up. Okay? So think about that. Also, if you increase the temperature, we already said the average velocity
being speed.
Speed, perfect. Speed, so if you want to add that, this is just speed.
This would be a great time to write velocity over in your key terms and speed with the definition next to it.
Perfect. And remember, guys, this is the perfect part of podcasting is you can pause us whenever you want. Go back. You know I talk fast, especially if I've had coffee. And yeah, pause us, okay? So as you increase the speed of the molecules, they're going to go up as well.
Now, if you have trouble remembering this with heat and with cold, think about what you guys do in the summer versus the winter. How many of you guys come into my classroom and just sit still because it's cold out? Like 50 degrees southern cold, not like 30 degrees New York cold. And in the summer, you guys move like it's nothing else. Way to remember it.
Miss Morris is from New York, by the way. And if you know me, I'm from Oregon. So we are not used to the heat.
No.
We're getting there.
And now, speaking of weather.
Difference between a hot day and a cold day. Well, Miss Morris, if I'm a gas molecule on a cold day, what am I doing?
You're just kind of chilling around, moving a little bit, but not a lot.
Man, I am freezing. My muscles barely move, so I'm just going to be like bouncing off a little bit. But if I'm on a hot day,
you are all over the place.
Check this out. I can balance my speed, my velocity, is all over. So gas molecules, remember, if you increase the temperature, if we go back, if you increase the temperature, the kinetic energy goes up, which means the speed goes up. So these molecules are moving at a much faster rate.
Now, if you guys are visual kids, go ahead and draw that picture, right? So cold day, low kinetic energy, low velocity, little arrows. Hot day, high kinetic energy, high velocity, big arrows.
And high speed. Okay? All right. Definitely include this in your notes. So if you want to pause this for a quick second, copy this down. You can do that now. What we're going to look at is we're going to look at the different speeds of cold gas and hot gas, but we're not going to draw it as the little molecules. We're going to draw it as a graph. So this is called the Boltzmann graph. And what we've got is we've got number of molecules on the side, and we've got speed of molecules on the x-axis. Okay? And temperature, you're going to learn, is actually the average speed. And so the average of a cold gas, right here, cold gas, is actually right. I can draw that down. This is the average speed. So if I had, it would be whatever units. It's moving at some miles per hour. And then this would be the average speed of my hot gas. So if I were to draw this with our little images, this would be something moving extremely fast. This would be something moving a little bit slower. Okay, so the number of molecules are actually the same because you can see here that this is an average. So there's a bunch of molecules down here moving at this speed. There's a bunch of molecules moving at this speed and a bunch of molecules moving at this speed. Remember what Ms. Morris pointed out in our picture, and I can go back to that. Not all of these are moving at the same speed, but there is some sort of average. So if we were to take all of these and then calculate an average, that average would be symbolized by this peak right here. So this is the average speed. Okay, and you can clearly see the hot gas speed. So the speed of the hot gas is much greater than the speed of the cold gas.
Again, same thing, just different ways of saying it.
Mm-hmm. Okay, so we're on to something different, a little bit like gas pressure. Now, you guys have all experienced pressure. On the sports field, whatever it is, you've experienced pressure to some of these. We have a very specific definition of pressure in chemistry. Now, gas pressure. Remember we talked about this. Picture this as a balloon. So we've got a balloon here, okay? A very good drawer.
Don't forget a string.
Yes, this is my string. We have Miss Morris. This is Miss Morris. We'll just call her MM right now, holding a string. This is her balloon. And we've got air molecules there hitting the inside of this balloon, and that's what keeps it blown up, all right? And when they hit that inside of the balloon, it delivers a force to that inside of the balloon. So that force, since it's hitting over a certain area, so you'll learn this, pressure is equal to force over area. We've got force, we've got the surface area of the balloon, that creates a pressure. So the more gas molecules that collide with the balloon, the higher the pressure. Okay, space, the final frontier. We've got a spiral galaxy, and you've probably heard the space is mostly empty. Not much up there, right? Okay, and actually as you farther get up, like if you were to take a plane all the way straight up like the space shuttle, there is virtually no gas.
No.
And so what do we call that?
So we're going to go ahead and call that a vacuum.
Vacuum. Perfect thing to introduce this into your vocab section.
Yes, we're going to go ahead and put that in our key ideas.
Yes.
And the other part in our notes. Now, this isn't a vacuum, like what you were going to go ahead and clean your house with.
No, actually spelled differently. This is, what your mom makes you do.
Saturday chores. Greatest part.
And that's
it's like a shoe.
I don't even know what that is. So a vacuum is double C. We're going to be talking about a different vacuum, and so next time space. So although this is a spiral galaxy and there are some gases in there where stars are formed, I'm a total astronomy geek, but it's pretty much empty. Okay, Ms. Morris, are you feeling a little pressure right now?
I'm actually okay right now.
You're feeling pretty good? I mean, it's Sunday. It's nice outside. Well,
it's not
nice
time.
outside. It's raining. We're going to call it a night here, but you're actually experiencing a lot of pressure right now.
Really?
Yeah, me too.
Okay.
You've actually got about 15 pounds of pressure on every square inch of your body. Seriously, if I was to take a square inch, a little stamp, 15 pounds. Imagine
Doesn't feel like it.
Guys, take a 15-pound weight and drop it on every square inch of your body.
Your foot preferably? No.
No, not your foot. That's why we wear shoes and lap, right? So we actually are all experiencing atmospheric pressure right now. and that is pressure due to the gases in the atmosphere. And we got a definition for that here. That's what it is, exerted by the air. So think about this. You're down here on Earth, okay, this is you, and if you were to look at like 1 meter, one column, so here's a meter by meter by meter, just a square block over our heads, it'd actually be over both of our heads, and we just lined it all the way up to space. Okay, there's a lot of air packed in there.
Yeah,
there is a lot
space
of air.
is a long way off.
Yeah, there's a lot of air, and actually that air, due to gravity, has weight. Okay, so you're tracking me right now?
Yep,
okay.
I'm following.
So this air that has weight is actually bearing down on us right now, and we can feel it. And if we were to add up all that weight and put it on a scale,
it'd be that 15 pounds, right?
Yeah, well, it's actually 14.7 pounds, and we're going to teach you how to convert, but that's where pounds per square inch. So you are under pressure. How does this pressure change? Well, it changes with altitude, and altitude, I'm confused. Altitude?
So altitude would be how high you go.
Exactly. So we can just kind of like say height. And that's the same thing too. So the higher you go, actually what happens to air pressure, what happens to it?
I'm thinking it's going to get a little bit less.
It gets less. It's tough to breathe the higher you go. And if you lived in the mountains, you would know that. But, you know, luckily we're near here sea level. So the higher you go, the lower the pressure. The lower the pressure. And we've got something to look at that. So this is Mount Everest.
Tallest mountain in the world.
Tallest mountain in the world. And if you've ever climbed Mount Everest, I don't plan to, but
maybe next year.
You would need some essential tools. Being,
well, you need some shoes.
Yep.
Some hiking gear, but more importantly, oxygen.
Oxygen. Why would we need oxygen up on Mount Everest? I mean.
Well, I'm thinking if the pressure is lower, it's going to be hard to take all that oxygen in. I'm going to have trouble breathing.
Yes, low pressure basically means low gas molecules, meaning not that many air molecules to breathe in.
So you're going to have to breathe more and harder to get all that oxygen into your system.
And here's a graph, so kind of familiarize yourself with this. I would like you to also sketch this just briefly. Make sure you have the tidal and the axes labeled. So we've got pressure, atmospheric pressure on the y-axis, and elevation, which is the same as height.
Now keep in mind, we've got units listed there. We've got kPa listed next to atmospheric pressure. Actually going to talk about that a little bit later, so don't stress.
We're evil. So
there are no even numbers.
Here's what's happening. So we've got height, and here's sea level, okay? And as we go higher from sea level, so think if you're at the beach in Mobile, and then all of a sudden you were able just to levitate up, I don't know, this magic space elevator, if you will, and you went up, you would find that as you went up, the pressure went down. And so it would get more and more difficult to breathe until the point where you're about 14,000 meters, which I think is Mount Everest. Or maybe I'm a little bit confused.
I won't disagree.
Yeah,
but I
think it's like Mount Everest height. There is only 20 kilopascals of pressure up there. So it's very difficult to breathe.
Considering that we normally exist at 101 kilopascals.
101, because like, let's say we're at sea level, right? So we're at sea level, so that's zero, or zero height. And we can go here, and it's almost exactly right there at about 101 kilopascals, right? So, okay, a barometer. Some of you may have heard of a barometer. We use them in weather systems a lot. They kind of tell us when the air pressures are different, where tornadoes might likely happen.
Yep, so the air pressures being different has to do with what the temperatures are and what kind of weather is going to happen. You're a meteorologist.
And what it is it's filled with mercury. And there's air pressure in here, and that actually keeps the mercury left in this tube. And you know what? It's just better if we just show this in a
Let's go ahead and do that.
Quick video clip. So let's go to the video clip.
Good to go.
Okay. Okay, guys, so we're going to make our little homemade barometer here. This is with water, remember? Normal barometers are with mercury. So I'm just adding blue food coloring, not because it's a chemical reaction or anything, but just because it'll be easier to see. So I'm going to mix this. I want to get it on Miss Morris's lab tables. Okay. And what I'm going to do is I'm going to invert this, and I'm going to put it, I've just got water here. If you can see, this is just water. And I'm going to stick it down there. You can come close and zoom in if you can see it. And the water stays in. The water doesn't flow back out because I was able to kind of sneak it in there. And so what's actually been created up here is a vacuum. Now what's happening, if you can see this, or you can come around if you want, we've got So gas molecules are constantly pushing and hitting this water, just like it's pushing on me and Miss Moore, so we're feeling the pressure. So gas molecules are coming in and pushing on this water. And when they push on this water, it creates pressure. And so by pushing on this, it forces the water to come on up. And this is going to equilibrate depending on how much pressure. So if I added more pressure and I was able to like heat up the room, if you will, like make it super hot in here and close it off, more pressure would come down, and then this level would actually go up. Now if it gets really, really cold in here, or there's less pressure, we were able to suck the pressure out of the room, what would happen was there'd be less pressure on the water, and then this level would go down. So depending on the height of this water column, we can actually determine the amount of pressure. And that's what we use with a barometer, which is out of mercury. Again, just to recap, kinetic energy is the measure of motion. The higher the temperature, the higher the kinetic energy. These gas molecules are moving all around. The lower the temperature, the slower they're moving. Okay? And gas pressure is just a measure of how many molecules are colliding with anything. So this table is feeling gas pressure right now because millions of air molecules are hitting.